Okay, I'm officially recording this meeting now, so if you're watching this, welcome. Um, Meeting is gonna start in like 5 minutes or so, so you get to enjoy this quiet period, I guess.
It's just us.
Yeah, it's not gonna show.
Oh,
I'm just screen recording the screen of which I'll be presenting. Oh, someone's about to join.
okay.
Hold on. So it's not gonna include our faces, but hopefully that's not too important. All right, people about to join in. Let me start presenting my screen as well. Welcome everyone. Sit tight. All right. Terry, you can see my screen, right? To make sure I'm presenting this correctly.
Yeah, yeah.
Okay, now it's full screen. Making sure. Okay. Hello, everyone. Just as a piece of information, I am recording this meeting. I'm recording my screen here, and I'll be uploading it like to YouTube probably as like a privated video. And I'll send it out after. So if you miss this meeting or you have to like leave halfway through or something, hopefully you can catch the rest of it when I upload it. But yeah. Welcome everyone. We'll be starting in a few minutes just to make sure everyone gets in here. And I am recording this meeting, and it will be uploaded hopefully right after this. So you can, if you have to like leave halfway through, you'll be able to catch the rest of it. Okay, we could probably get started, Terry.
Okay, all right. So I guess welcome everyone. Today we're gonna cover Electrochem 1, and this is the first part of Electrochem. We're probably gonna cover the other half of Electrochem sometime later. And Electrochem is really important on the exam. It's probably like 7 to 8 questions. And then you guys like won't cover it in AP Chem, so we think it's pretty important, and then so we're deciding to cover it this early. And then also like if you have the Zoom textbook, if you look below, this is a chapter that you want to read. Yeah.
Oh yeah, wait, Terry, say about the thing that Miss Bardo was just talking
Oh
about.
yeah, yeah. So if you guys don't know, Kennesaw State University this year is hosting like I guess a review session for like 10 people at like every school. Like don't you have to go talk to Miss Bardwaj about it, and then like she'll like put you on the list of like the 10 people, and then like Kennesaw will help you prepare for the national round. And so yeah, if any of you like are interested in that, you guys should go definitely go talk to Miss Bardwaj. I think there's like 2 spots left in that list.
Mhm. Okay.
All right, so this is a review from the last meeting. So you guys can like type the answer in chat or like say it out loud. Okay, so it's actually okay. So actually on the Olympiad, it's B. It's a graduated cylinder. So like so generally beaker is like the least accurate. So if you want precisely as possible, you want to select the beaker. But like generally on the Olympiad, almost every single one of these questions is actually graduated cylinder.
Okay. Uh, so yeah, so keep that in mind, I guess. All right, we'll start
Yeah.
now
Yeah.
with.
How do we determine that again?
Generally it's kind of you don't it's just kind of something like you just have to like know. It's just like whenever they really ask you this question in the like literally the past like 10 something years they've asked this question, it's literally always graduated cylinder. And for this one it's graduated cylinder too.
So
Yeah,
when is a beaker then?
Sorry, what was that?
When is a beaker?
Beaker, well, okay, beaker is like if they were to ask you like the least precise method, it would probably be beaker. But they almost always ask for like the precise as possible, and it's generally okay if they give you between a volumetric pipette and a graduated cylinder, go for the volumetric pipette. The volumetric pipette is the most precise out of all the options it would ever give you, and then second would be graduated cylinder, and then generally everything else is irrelevant.
Yeah, I think the volumetric flask is supposed to be for holding a specific amount of liquid. Uh, but like if it's not that amount of liquid, then it's not going to be more accurate than the graduated cylinder. At least if I'm Googling this correctly. So I'd assume in this case, if it was asking like, oh, the student needed 25 milliliters of liquid, then you'd probably go with a volumetric flask. But since it's not, it's 12 milliliters, then it's going to be the graduated cylinder. Okay. All right. So sort of starting off this conversation about electrochemistry. Um, First, what is even the point of electrochemistry? It's sort of a tying together chemical reactions with the flow of electrons, which is like electricity. And so I sort of have here a example from the book. By the way, like a lot of the images here are going to be directly from the Zoom textbook. And so if you want more information, read the textbook. But But so you should be able to recognize when you see these sort of reactions that there's sort of a flow of electrons, a flow of charge, I guess, happening between the elements. And so you can actually split up this reaction here into what's called half reactions, and one of them is a reduction and one of them is an oxidation. And so a reduction means that the oxidation state on the element is decreasing, while an oxidation means that the oxidation state on the element is increasing. And so you can see it's pretty clear, I think, for the oxidation of the iron here, what's happening. On one side, it's going from with a +2 charge to then a +3 charge. And so that's why you have sort of this electron here as to kind of keep that equilibrium of charge on the product side. Because if you add up the charge here, it's also +2, which is the same as this side. But the iron itself is increasing its oxidation state. While for the reduction here, if you focus specifically on the manganese, that Mn, here it has a charge of +2, and here it's going to have a +7 charge if you actually work out like sort of the quick algebra behind it, where oxygen is a -2 charge and then overall it's a -1 charge. It comes out that the manganese here is a +7. So it's going from a +7 charge to a +2 charge. That means the oxidation state is decreasing, and that's why you have also these 5 electrons here to account for it. And then finally, you can sort of see here the coefficient for this half reaction is 5, so that the electrons cancel out. So in this half reaction, you have 5 electrons in the reactants, and then here you have essentially 5 electrons in the products, and so that's why they cancel out and they don't really show up in our overall equation. But you should still be able to then see that there are flows, like a flow of electrons happening here in this reaction. Okay, so then how can we use that? So be ready to like memorize this word, galvanic cells, because there's another type of cell that you have to know. But galvanic basically is going to be looking like this, and get ready to also like see a lot of these types of pictures where it has like sort of these 2 beakers and then they're connected in some way. And so let me sort of describe what this picture really is representing, what each component of this picture is, as well, and use this example here, this example reaction, to kind of go through that. And so again, if you notice this reaction, you sort of see that the zinc here is going from a neutral charge to a +2, while the copper is going from a +2 to a neutral charge. So again, you're seeing a difference in charge between the reactants and products for each element. So how can we use that to make a flow of electrons happen? So you're going to have what's called an anode and a cathode, and the anode is this beaker here on the left side, and the cathode's on the right side. And here the anode is going to consist of the zinc in solid form, and the reaction that's happening here is that it is sort of ionizing, so it's sort of dissolving. So you can see the reaction here that is happening, that the zinc is well, it's being oxidated basically because it's going from that neutral charge to that +2 charge, and it also, because this reaction is happening, it is also giving off 2 electrons. Okay, and that's going to be important. And so if you sort of follow through with this reaction, you're going to see that basically your solid is going to be slowly dissolving as it becomes like an aqueous species here in this beaker. So then what about on the right side, on the cathode? It is sort of the opposite reaction. You have an ionized species that's here, like in the solution, that is becoming solid. And so it's accepting the electrons that are flowing from the anode, as you can see here, going through that wire. And so the ionized species here, the copper, is going from 2+, and then accepting those 2 electrons to become neutral charge, and it becomes solid. And so here what's happening is a reduction, because again the charge is decreasing from +2 to neutral, which is 0. And so you'd notice that sort of what's happening is the solid is slowly being built up. And down here in the bottom corner, you can see sort of a zoom of what's actually happening on each solid. So again, you can see that the solid zinc here is sort of like splitting off into an ion and then 2 electrons, and the electrons are conducted through this wire here. While on the other side, it's the ions that are coming in and they're accepting the electrons from the wire to form the solid. And finally, the last component of a galvanic cell that you need to keep in mind is what's called a salt bridge or a porous disk. And it's this thing right here. And I think this one is called a porous disk. A salt bridge would be sort of a tube that's above the beakers. Honestly, I don't know which one you're supposed to go with for which scenario, but you're going to see both. And sort of what you just need to know about this is usually not too much more to know about this is that it keeps the charges sort of balanced, so they don't have a buildup of charge, and it does this through like a migration of ions, so that you're not like getting like a bunch of positive charge here and a bunch of negative charge here or something like that. So those are the components of a galvanic cell, and we're going to see sort of how we can. This is like a physical representation of what this would look like, but now you're going to be able to sort of have to take these sort of reactions, understand that it's sort of a galvanic cell here in the sense that there's a flow of electrons and two half reactions happening, right? There's this reaction that's happening here and this reaction that's happening here, and sort of predict whether it's favorable or not. So this is sort of the information that I've talked about again, but sort of in a more slightly structured layout. So anode is going to be your oxidation, and usually I memorize that because they both start with vowels. And also you can think of the electrons are sent away, and so that A here matches up with the anode. And this is where the solid becomes sort of aqueous. And then the electrons flow from the anode to the cathode, so they flow away from the anode into the cathode. And so I guess what you can memorize here is that they both start with consonants here, the cathode and reduction, and also electrons are being received, so those R's match up. And if you remember like Leo goes grr or whatever in like oil rig or whatever, that might help you memorize it as well.
Yeah, so there's actually two different types of cells. So there's like Nino said earlier, there's the galvanic cell, and then there's the electrolytic cell. And basically like what these cells are is the galvanic cell is where you convert energy from a spontaneous redox reaction, and you convert that into electrical energy. So like an example of the galvanic cell would be like a battery, and then you have the electrolytic cell, which is the opposite, where like you have where electrical energy is like used to drive like a reaction. An example of this, like if you like want to break up water into oxygen and hydrogen, you would use like an electrolytic cell to do that. Yeah. Next slide. So for electrolytic cells, what you have to consider is like there's a couple possible different reactions that can happen on the cathode and an anode. And then on the chemistry Olympiad exam, it will like ask you to predict like what will happen at the cathode and what will happen at the anode. So for the cathode, you have to consider a possible reduction of water. And then so if your cation on your cathode is like not is like really weak, then like a reduction of water will happen instead. And then also for the anode, you have to consider like several different possibilities for what possibly could happen. Next slide. So like if you follow these guidelines like here, this might be something you want to memorize. Like you'll basically know what gets produced where. And then so cations of less active metals. So like a lot of the d orbital like metals and stuff are like not as active, and they are reduced on the cathode. And then also the anions of less active nonmetals. So like a lot of your a lot of your like iodine, bromine, like, and then stuff like that are oxidized on the anode. And then also cations of like really active metals are not reduced, and then anions of nonmetals are not oxidized. And then so if you follow this general order, you'll be able to predict pretty much what happens on the cathode and anode. So there's actually a question on the next slide. So like based on the previous slide, if you read the guidelines, like you guys can try to like answer what exactly you guys think will get like predicted on the cathode. So cathode is reduction.
Terry, do you want me to go back to the previous slide?
Yeah, you guys can reference the previous slide. So it's HEF, and then based on the guidelines.
let me quickly go back to the question so you see what the answer choices are. Okay, does anyone think they have like an idea what this answer is?
No, that it is A. So okay, so if you look at this AGF, and then if you go back to the previous slide, it asks you what's formed at the. Okay, I think that's the next slide. Let me go back. Yeah, this slide. Okay, so it asks you what is reduced on the cathode. So it tells you right here that cations of less active metals, and it actually gives you the example Ag, so are reduced on the cathode. So it's not any of the other choices, and it's Ag would be the one that is reduced. And so based on this chart, if you go back to the question itself, so what do you guys think like LIF would be? The same thing, like what would be formed on the cathode during electrolysis? Maybe you can go back to like the previous slide as a reference. Yeah. So it's LIF, and then what would be reduced? Yeah, that's right, Liam. So basically, Li is like a really active metal, so it will not be reduced, and then H2O is reduced to H2 instead, based on the third rule here.
Yeah, so we'll probably cover a little bit more of electrolysis when we have the second part of this lecture. But we sort of just wanted to introduce that there's like two types of cells. There's the galvanic and the like electrolytic cell. But we'll probably talk about more of that in the future as well, because these are I found that usually there's like these questions are the tough ones, and so we should probably spend more time on that for sure. Okay. But sort of going back a little bit now to, well, actually this pertains to both types of cells, but we're going to be thinking about this again in the context of a galvanic cell, which is where a spontaneous reaction is happening, so thermodynamically favored. So cell potential is sort of again a measure of how likely a reaction is like to happen, is essentially how we're going to use it. And so in this case, the cell potential is sort of what's measured here in this voltmeter. And so that's as electrons are passing through, it spits out a voltage, which here is 0.76. And the way that that's going to be useful to us is that then we're going to be able to sort of predict what reactions are likely to happen or not likely to happen. But to first start with that, we want to measure the voltage of each half reaction that is happening. Okay, because later when we put in like two different elements, like down here we have zinc and copper together, we're not going to be able to predict what the voltage of that is unless we know individually what the voltage is going to be of a zinc half reaction and a copper half reaction. So how do we go about doing that? So I guess chemists started off by doing this type of reaction where they had zinc reacting with hydrogen or H plus here to then, and you can see the zinc here becomes oxidized, it becomes aqueous while it produces H2 gas, and so that's what's happening here in this photo, if you can see. So they had this sort of reaction happening, and again, this consists of two half reactions. This consists of the zinc becoming oxidated here, while the hydrogen is becoming reduced. But so what I guess chemists sort of arbitrarily decided in a way was that this half reaction of 2H plus becoming H2 gas was going to just be arbitrarily assigned a voltage of 0. Okay? And so if now we say that this voltage is 0 of the half reaction involving the hydrogen, but we know the overall reaction has a voltage of 0.76, then we can assign that the half reaction of zinc to of solid zinc to the aqueous ionized version of zinc as having that voltage of 0.76. So it's sort of like algebra. Here you can see that the overall potential of the cell is 0.76 volts as measured by our voltmeter. And this consists of two half reactions. But one of them we're just going to say, okay, this is 0. And so that means the other one's 0.76 because this half reaction isn't really that useful for other things. We're more interested in figuring out individually what the half reaction cell potentials are for the zinc here. So we can determine this now, that zinc has a voltage of positive 0.76 volts. So with that information, now if we have another half reaction happening instead of, so before the hydrogen here was being reduced, now it's going to be copper that's being reduced from 2 plus to neutral, so 0. And we are told here in this image that the overall voltage of this reaction here is 1.1 volts. And so again, sort of using the same algebra from before, we can now deduce that since the half reaction that consists of zinc going to the ionized version of zinc is 0.76, then the other half reaction must be 0.34 volts. Okay, so sorry, this is showing up over the thing, but basically now we also know that what the voltage of this half reaction is of the Cu 2 plus becoming the solid version of copper. We see that has a voltage of positive 0.34 volts. And so using that, we can figure out basically the voltage of a bunch of half reactions. So you can see this table here that was from the textbook has listed a bunch of half reactions. So it's just a element becoming reduced. And so these tables are usually given with only reduction potentials. So only a reduction reaction is happening. And so you can see here, this is the copper half reaction we were talking about before. It becomes reduced. It goes from 2 plus to 0. And like we said before, that had a voltage of 0.34. But what's interesting is that we here have the zinc reaction that we were talking about before. But now instead of being positive 0.76 volts, it's negative 0.76 volts. Because if you remember in the previous slide, the zinc was actually being oxidized. It was going from solid to aqueous. And so that half reaction has a positive 0.76 volts. But if we're doing the reduction, which is the opposite, then it's going to have also a negative sign attached onto that. So that's why you have a bunch of negative signs here on some half reactions, and then other reactions are positive. But keep in mind that these tables are usually given in only reduction potentials. Okay, so now sort of tying back to what we had originally when we had zinc and hydrogen, and then we used that to figure out what zinc was, and then we plugged in zinc for copper. Once we have this information, we can sort of now do the reverse type of calculation, where if we have the voltages of the half reactions, we can figure out the overall cell potential. Okay, and so that's going to be sort of a lot of the math that you're going to be doing on questions. And so this is sort of a pretty helpful formula, is that the overall cell potential, and that's what this weird E looks like, or that's what it's supposed to mean as the cell potential, is going to consist of the cell potential at the cathode minus the cell potential of the anode. So this is basically saying the cell potential of the half reaction that's happening at the cathode, which is a reduction, minus the cell potential of the half reaction that's happening at the anode, which this should say, I'm pretty sure this should say, oh wait, no, I think it's fine. This is a reduction as well. So you sort of shift around, since in the anode what's actually happening is an oxidation, you have to then sort of undo that and flip the sign on that to make it a reduction, and then you can sort of do the calculation. And so sort of going back to this, we were told that the reduction potential of copper here was positive 0.34 volts, while the reduction potential for zinc was negative 0.76 volts. And so if you then do the math and plug it into these formulas here, you get positive 1.1 volts, which is exactly what we had in the 2 slides ago in the voltmeter. So that's sort of how you can, and that's more often what you're going to be doing is working with half reaction potentials and putting them together to get an overall cell potential. And so, again, this is sort of, I've already explained this part, that the cell potential of a reduction half reaction, oh yeah, crap, I forgot to change that. That should say oxidation. Basically, when you're going from reduction to an oxidation, so you're flipping sort of the reaction, you're also going to be flipping the sign of your potential there. So definitely keep that in mind because you're definitely going to need to use it. And so here's another way of expressing the formula we had before, but now we sort of, if you see here, I changed the sign here from negative to positive, so you're adding both of these half reaction potentials, but I'm also changing this now from reduction to oxidation, since doing that changes the sign. So these two formulas are basically equivalent. It just depends on what sort of information you're given, or which one is like quicker for you to use. And so yeah, you can do sort of the same calculation that we did before, because if you remember, if I go back here a couple slides, we said that the oxidation potential for zinc was positive 0.76, while the reduction potential for copper was positive 0.34. And so once again, we could use those numbers directly instead of having to worry about flipping signs to get the same answer that we had before. And finally, in terms of sort of calculations I have to do, this is actually really simple. Not every half reaction, or not every cell, redox reaction that you have is going to be sort of like this, where it's like very even, where you have one of the zinc and one of the copper. A lot of times you're going to have, and at the beginning of the slides, we had a reaction where you had to have a coefficient. The great thing is that even if you have coefficients here, which you can see in this reaction where it's copper plus iron, then you split that off into two half reactions, and then you can see that there's sort of, to keep them balanced, you'd have to put a coefficient here. That doesn't actually change the potential at all. So you don't have to worry about coefficients. All you have to worry about is whether your half reactions are a reduction or a potential. And so if one is a reduction, another one's a oxidation, then you can just add them together. If they're both reductions, then you have to subtract one of them. So again, those are sort of equivalent algebraic things that you're doing. But yeah, and so with this example here, if we work this out again, so we have this overall reaction, which has been balanced for us, which is good. And so then we can split this off into two different half reactions, and it doesn't matter that we sort of get rid here of the coefficient that was on the iron, because again, for the voltage calculation, it does not matter. And so we're told we can look at, like, usually they're going to like give it to you, the voltage of these half reactions, that the reduction of iron here is 0.77, and that's positive, while the reduction here of copper is 0.34. So we have two reductions here that are both positive, which is sort of interesting. We didn't have that before. And so if we now sort of tweak these half reactions so that one is an oxidation, one is a reduction, you can see here that we flip the copper half reaction. And so since we're flipping the copper half reaction, we also have to flip the sign on the half reaction voltage for that. And then when we add these two, then we get this overall cell potential. And I believe Terry's going to be talking about this slide. Oh, no, I'm talking about this slide, sorry. So with that, if you can take these half reactions and calculate the overall cell potential, okay, why is that important? A galvanic cell, for the reaction in it to occur, and really for it to be a galvanic cell, then the reaction that's happening must have a positive overall voltage, an overall positive cell potential. And so far in these two examples, this was positive, and previously this was also positive. So both of these reactions were thermodynamically favored. They were going to occur. And the more positive the cell voltage, the more thermodynamically favored it is. And you're going to see later there's sort of these equations that you can use to connect this to equilibrium and Gibbs free energy, which are other topics in chemistry. And sort of another miscellaneous thing is that sometimes you might not have a solid becoming an ion, for example, or an ion becoming a solid in one of the half reactions, but maybe it's just an ion remaining an ion, but the charge is still changing. So in this example here, you can see that the manganese oxide here, this is an ion, and it becomes just a manganese ion. But there's still sort of a change in charge here. This is a reduction that's happening here, but none of those are actually a solid. And so when you have that, you're often going to see what's called like an inert electrode, which is here, this platinum here. And that sort of helps conduct the electricity, but you're still that they're not going to be used at all. You don't have to worry about the platinum in terms of like what the reaction, the half reactions are. Just focus on the species that are actually changing their charge, but just keep in mind that you have sort of this inert electrode here to help conduct that. And where that inert electrode sometimes comes from, or where it might be used, is if you're ever looking at line notation. And so that's what you see down here. And so that's a way to sort of, instead of having to draw out this beautiful diagram here of a galvanic cell, they use sort of what's called a line notation, where they have, and you can see here the overall formula for it. They have the solid that's at the anode all the way on the left side and separated by one bar, and then the ions that are at the anode. So again, here on this left side. Then you have two bars to sort of represent that you're splitting off into now going to the cathode and sort of the emitter. So then you have the ions on the cathode and then the solids that are at the cathode. And so in this example here, you can see I have included here the line notation. We have solid iron here on the anode. Then we have iron like ions here. And so that's why you have that there. Then in the solution here of the cathode, you actually have two different types of ions, which are both listed. And then finally, the solid here is going to be your platinum, which is the inert electrode, although it's not involved in any of the reactions themselves. Okay, so that's a lot, but sort of understanding what's happening in terms of like an overall reaction being half reactions, and then also being able to calculate the overall cell potential is pretty important. Okay, so I think Terry's talking about this slide.
Yeah, so this is a pretty critical equation in electrochem. A lot of other equations, such as like the Nernst equation, is like derived from this, and then basically like, which I don't believe this exact equation is provided on the exam formula sheet. So you likely have to memorize this, and then basically what it is your free energy is equal to N, which is number of number of moles of electrons that are being transferred, and then there's this Faraday's constant, which is 96,485. But like you don't need to memorize the exact numbers, as long as you know it's 96,500, it's fine. And I believe the number is like provided on the Olympiad. So I don't think you need to worry about memorizing this constant at all. And then E is your cell potential. And then so here basically if you have a positive, like what you can gain from this equation, if you have a positive delta G, that equals like a negative cell potential, which means it's not thermodynamically favored. And then a negative delta, so a negative difference in free energy, and then a positive equals a positive cell potential, and then that is thermodynamically favored. And then basically for your K, as long as it's greater than 1, is thermodynamically favored.
Yeah, and that's sort of a connection to equilibrium. I don't know how much you guys remember about equilibrium.
Yeah, that might be something you guys will like learn, I think, in like January or something. So like, yeah, generally don't worry about the equilibrium stuff until then. And then like this is an example of like how the previous equation like works. So you have this equation up here, the copper ion plus iron, and then you have the solid copper, and then the iron ion, and then you have the cell potentials, and then what you have the potential at the cathode and the anode, and then and then combining that, you get the cell potential, and then you can find the difference in free energy with this equation. So how you get so if you look at the very bottom, the picture at the very bottom, how you get the two is because you have two electrons being transferred. You can see that from the second picture there. You have two electrons being transferred, and then you plug in the 96,485, and then this again like I said earlier, this number you can substitute with 96,500. It's pretty much the same. It's like a very minimal like error you'll have. But, like I think the Olympiad wants you to use 96,500. So I would probably memorize that number, and then you have the 0.78 from your calculated cell potential, and then that's how you get your difference in free energy. And then there's quite a lot of questions on the exam that will just directly ask you like calculate difference in free energy, like given all these like constants, and like if you know this equation, those should be like pretty easy. This is a practice question from the 2020 exam. So I guess just like type your answers in the chat, for like you can like say them out loud. Yeah, for this question, try to use the equation like I showed in like the the previous slide, and then like just like plug in. It gives you pretty much everything you need like here in this table here, and you can just like plug it in, and then just see what you get. Yeah, the answer is C. I think. Go to the next slide. Yeah. Yeah, the answer is C. Basically, again, you just you can determine this based off like the cell potential here, and then you kind of just like you kind of look at this like this equation they listed in one here, and then you can create that with the half reactions, and then you can determine if it's spontaneous or not. And then for the second one, it's basically the same thing. You can create the second one with the half reaction that they list in the table here. And then yeah, so the correct answer is C. Both 1 and 2 are spontaneous under standard conditions. And then additionally, maybe like which one do you think is product favored?
Or more specifically, which one is going to be more product favored, where the products are like way more favored than the reactants are? So for this question here, you'd have to look at the overall cell potential. So here you have a overall cell potential of positive 0.8, and here it's positive 0.06. So clearly this one, the voltage here is bigger. And if you look down here, oh, whoops, hopefully that thing goes away. Okay, I have two equations here at the bottom. One of them you've already seen, that delta G is equal to negative NFE. But that other equation is probably you have not learned it yet. and it has to do with equilibrium. So again, if you haven't learned equilibrium, then don't worry too much about this yet. It's just a equation that relates free energy to the equilibrium constant, and the equilibrium constant is just talking about the ratio between products and reactants essentially. And what to take from this is that it shows that if you plug in both formulas together, an increase in cell potential means an increase in the equilibrium constant. So essentially, the more positive a cell potential is, the more the products will be favored. But again, keep in mind, if the cell potential is negative, then that means the reactants are favored, and the reaction overall is thermodynamically disfavored. But yeah, I believe that's it for this. It's sort of, we haven't gone even too math heavy yet. These types of questions here, like number 39, I mean, this was on the exam last year. These are things that hopefully you'll be able to get 100%, because this is honestly a really, really simple question. It's just doing like 2 calculations and that's it. But in the next lecture that we do about electrochemistry, we'll talk a little bit more about the Nernst equation, which is a little bit more complicated. But this sort of stuff, it's pretty important to have a really good grasp of what is happening here. And we understand it's a little bit tough to sort of learn this in like 45 minutes that we've tried to do here. So if you want, read the textbook chapter 18. And if you need help on like how to access that textbook, then you can like message me or Terry probably to get access to that.
Also like for next meeting, I think it's probably a good time for you guys to like go over the 2000 local exam. That's probably the easiest like previous exam they have. Like it's the difficulty has scaled up by the years. So yeah, work out the 2000 local exam, and then if you guys have any questions, just send it to us, and then like we can go over it next meeting, or and then we can like help you like answer some of them. So yeah.
So yeah, there's gonna be, if you're really serious about becoming a finalist and potentially even getting like honors or even reaching camp, then you're just gonna have to do a lot of like studying at home. Is gonna be the truth. And so doing practice exams is a great way. They're all available on the Chemistry Olympiad website. If you just search Chemistry Olympiad US, you'll find that they have posted pretty much every local exam for like 2 decades at least or something. And so try to do those at a regular pace. Right now, you probably don't know too much, so that's fine. But sort of see it as a diagnostic and see if you're good at the questions that you're supposed to know. If you're doing well in questions that you are supposed to know, then obviously that's really good. But don't sweat it too much if like certain electrochemistry questions or the organic chemistry questions you don't fully understand yet. That's okay.
Okay. Do any of you still have any like questions from either today's meeting or like from the meeting last week we had? Like, do you still have any lingering questions related to like how the Chemistry Olympiad works, like what to study, stuff like that? Okay, well, I guess we'll just end it there for today, and then Nuno and I will like stick around if you like still have any questions.
Mm-hmm.
Oh, actually, I do have a question. I wasn't here at the first meeting, but wait, can you hear me by the way?
Yep.
Okay.
Yeah, we
So
can hear you.
what's the format of the exam? Is it just test questions? Is there like a physical portion, or like how is it formatted, I guess?
So for the local exam, you're taking, it's simply just multiple choice. It's 60 multiple choice questions. So yeah, you don't really have to worry about any like lab stuff, FRQ. That's mainly stuff you have to worry about in like the next couple rounds. But like you have sufficient time to like prepare for that after you like find your results from the first round.
And do you like okay, so you said like there's multiple rounds. Do they get harder as you go on, or is it just like
Yeah, they get harder. So after like, so basically on the local exam, if you like score about a 40, I would say like if you score above 45, you probably will make it to the national round, and then you become a national finalist, and then from there you're facing off with like the top 1,000 people in the U.S. For the Olympiad, and then that is like the really hard stage. That one there's like three parts. There's a MC part, there's a free response part, and then there's a lab portion, and then all three of those like yeah, generally if you like I wouldn't really stress about the other parts like until like after you find out your results from you have about like a month and a half. Like if you make it to the national round, you have about a month and a half to prepare for that. And then that will determine like if you make camp. They also have like an honor. They also like list the top 150, top 50, and then the top 20 people make the camp, which is where like you go to like some university over summer and like you prepare for the international chemistry Olympiad, and then you could potentially get selected for the U.S. team, which is like I think four people and one alternate, and then you guys like go to some like country to like compete. This year it was like Turkey. Yeah, they hosted in like a random country every single year, and then to compete. But generally, like at this point, you should mainly just focus on like taking the past local exams, and then like because like mainly you don't worry about the multiple choice for like right now. And then also yeah as you can see here like the thing is like chemistry Olympiad has like a weird restriction that like only two people from a single school can make it, and then so like potentially the cutoff could be higher if all of you guys do like really really good, but a maximum of 13 people from so the top 13 people from the state will advance. Yeah.
Yeah, and keep in mind, last year Terry and I both made it. This year we don't. We definitely do not plan on taking the exam and potentially taking the two spots. So there's two free spots basically open from Lambert to qualify for nationals. So yeah, definitely can be competitive this year.
Yeah, but you have to like meet the minimum cutoff for the state first. After you meet the minimum cutoff, if there's like more than two people per school who advance, it's just like which two people have the highest higher scores.
Yeah.
So
If Terry and I do a good job this year of teaching you guys, then maybe we'll run into that problem of having too many good candidates, unfortunately. But any other questions? You can type them in the chat as well. Because if not, then you guys are free to leave. Our next meeting will probably be like early to mid-November, I think is what we're planning. And we're honestly not too sure yet what we'll cover. We still plan on, of course, finishing up electrochemistry. We want to talk a little bit about organic chemistry at some point, and then also talk about like miscellaneous topics that aren't covered in AP chemistry, but they're not like super big or anything. And then hopefully that will cover sort of everything that's on the open exam at least, and hopefully many of you have a good shot at making nationals this year.
Thanks, guys.
All right, thank you for coming. All right. I'm also gonna end the recording here. Hope you guys enjoyed the recording. Hopefully nothing messed up. If not, then I'm gonna be pretty embarrassed.